All right. So the other day when we were looking at this, I had the graphs made for you. I went into Excel, graphed the concentration versus time, and then I graphed the natural log of the concentration versus time, and then the inverse of the concentration versus time. You have to graph all three graphs. One of them should be a linear graph, and that's the one that's going to dictate or determine what order the reaction is. It's either zero order, first order, or second order. Now, this one we determined, I still have those graphs here. This is not the right problem, though. This is the right problem. The H2O2 decomposition, we can see even without expanding it, this is not linear. And the second order graph, the inverse of the H2O2, is not linear. This one is linear, and in fact, it's very linear. We can see, and I don't have it up here, if I display the R squared value, that again is called regression, that says R squared is 0.9998. It's very linear. So we can tell that it's first order, and therefore, the integrated rate law for this one would be natural log of the hydrogen peroxide concentration equals negative KT plus the natural log of the initial concentration. This is the first order integrated rate law. So I didn't do any more with this other than to tell you this is what the integrated rate law looks like. When we go back to the question, though, here's what it's asking us for. It gives us this data, and it says, determine the rate law, comma, the integrated rate law, comma, and the value of the rate constant. Now, there's two rate laws, as I told you the other day. There is the integrated rate law, but there's also the differential rate law. When it says find the rate law, and it doesn't tell you which one to find, it implies that they're talking about the differential rate law, which we haven't done enough with yet to come up with. Next week, after we do the experiment on Monday, on Tuesday I'll start talking about differential rate law. So for right now, we're just going to focus on the integrated rate law. So I'm going to not be able to answer that, but we could answer it, but it doesn't mean as much yet. So we found the integrated rate law. It's here. That is the integrated rate law. It says, and find the value of the rate constant. Now, I want to remind you that when we have a rate law, no matter which one you have, you either have the zero order, first order, or second order equation, they're all three going to be in the form of a straight line. Remember, you're going to choose which one is the linear graph because it's going to have the form y equals mx plus b, the equation for a line. Now, the slope is the k value. I want you to notice, I'm going to go back to it. Sorry for all this jumping around. I want you to notice that we're monitoring the concentration of the reactant. The reactant starts at a certain value, and then as the reaction proceeds, the reactant gets used up. So notice that with the zero order graph, even though it's not a straight line, it goes down. It starts high. Remember, the initial concentration was 1, so it starts at 1, and then it goes down because the hydrogen peroxide is getting used up. Well, as the H2O2 gets used up, the natural log of its concentration also is going down. So as the concentration is going down, the natural log of the concentration is also going down. So the zero and the first order always have a negative slope. The second order, though, keep this in mind, as the concentration goes down, the inverse of that number will be going up because the denominator is getting smaller for this. So the second order graph will always have a positive slope. Now I want you to notice I'm going to have a couple other problems that we're going to do just so that we can see and compare. This is a different problem, but the same thing was graphed, the concentration of the reactant. The zero order graph went down, the first order graph went down, the second order graph went up. Here's our last example. This is really tiny, but you can see zero order graph is going down, first order graph is going down, second order graph is going up. So if we're monitoring the concentration of the reactant, which is always what we do when we do an integrated rate law, the rate law for the zero order is negative KT, the graph for first order is negative KT, but second order is positive KT because it's a positive slope. Yeah.
So, are 0 and first always down or can we also go up?
No, they have to go down.
Okay.
Yep, they have to go down. The K value itself is always positive. K is called the rate constant. The value of K tells us if the reaction is fast or slow. The bigger K goes, the faster the reaction is. So the slope, how steep that slope is, or whether it's going up or going down, how steep the slope is tells us whether the reaction is fast or slow. The steeper the K value, or the higher the K value, the faster the reaction. Now I do know that there's a negative sign out in front of there. When we have 0 in first order, there's a negative KT. But please know that K value itself is always positive. Don't ever give me a negative K value. It means that the rate is negative. You don't have a negative rate. The concentration may be going down, but the rate of the reaction is always positive. So yeah, that is just to account for the fact that 0 and first order have a negative slope. Okay. So if we can find the slope of the line, then we have the K value. Now we can, now this is not the one that we were doing. Here's the H2O2 problem. We have this line. You could take your calculator just like you did in the reading quiz and find the difference in Y over the difference in X. Or you can save yourself the trouble and have the computer do it for you. And I already have done that. In my little trend line menu over here, one of my options is to display the equation for the line on it. So it has it over here. You probably won't be able to see this, but it gives us the equation of line Y equals negative 0.0008x minus something very close to 0. So it gives us the K value. It's telling us what the slope of that line is. So these problems turn out to be very simple to do. You have to make the 3 graphs, have a computer do it for you, or your calculator, or Desmos on an iPad, or whatever you like to use. Put in the data points, have it graph it for you, have it tell you what the equation for the line is, and then that gives you the K value. It just gives it to you. There's no calculating or figuring it out. The thing does it for you. So going back to the problem. So it says find the value of the rate constant. If you remember, the rate constant in that one was K equals 0.0008. That's all. They only gave 1 sig fig, so that's what we have, and it's fine. Now there is a unit on K. It's going to turn out, we'll talk more about the unit when we do the other type of rate law, the differential. But K has a unit, but it depends on what the order is. So K's unit in 0 order is one thing, first order in K is a different, second order is a different. So it turns out this one is first order, so K has the unit 1/2 when it's first order. But I just put that there because I hate looking at numbers that should have a unit not having a unit. So that really is for my edification. You just need to know, we will worry about the unit on K when we get a little bit farther. Now, it also asks us a bonus question down here. We're asked to find 3 things: differential rate law, integrated rate law, which we found, and then the value of K. We found that. The 4th thing that it asks us for is, okay, well, what would the hydrogen peroxide concentration be if we went this thing out, or we allowed it to go out 4,000 seconds? You can see in our data, we only went out to 3,600 and then it stopped. But what if we went 4,000? If you need the concentration at some time, you have the rate law, which is a mathematical equation that describes the rate of the reaction. So the integrated rate law gives us the relationship between concentration and time. So if we know what that relationship is, and we do, it's right here, then we can put our numbers into it. K is a constant, that doesn't change. So what is the hydrogen peroxide concentration? We're looking for this thing right here. So we do natural log of the H2O2 equals negative K, which is right here, 0.0008, times the time. The time is 4,000 seconds. We're just putting our numbers into this. Plus the log, this is the second time I've done that, natural log of the initial concentration, which we have. The initial concentration was 1. Okay, now we are going to need to solve for this thing. This is going to be different. My Algebra 2 students, you have not done this yet. I tried to protect you in chapter 17. We had those natural log problems. I was allowing you to take your calculator and just enter in natural log of a number. But that was all we were doing with it. We weren't, if you like, had the natural log of k, but you didn't know what k was, and you had to solve for it. I told you to omit those problems. We didn't do those. But now, it's time. We're going to move along, and I'm going to show you how to do that. When you take the natural log of a number, like the ln of a number, I'll just call it x. What that means is e, the number e, as I told you before, e is this number based on factorials. E raised to what power equals that x? The natural log of x means e to what power equals that number. So we just have to figure out what the exponent is on the e. Just like log base 10 is 10 to what power equals that number. When we take the natural log of a number, we're saying e to what power equals the number. So let's go ahead and solve for the H2O2 concentration up here. I'm going to go ahead and get rid of all this other stuff. It's done what it had to do. So now up here, we have all the numbers on the right side, so let's go ahead and do that. Negative 0.0008 times 4,000. Negative 0.0008 times 4,000. Plus the natural log of 1, which is what? E to what power equals 1? Even if you have never learned about logs yet, you could still answer this question. E, some number to what power equals 1? 0. Zero power. Any number to the 0 power equals 1. So this term is 0. The natural log of 1. E to what power is 1? 0. So, let's see. Oh. So my right side is negative 3.2. My left side is the ln of H2O2. Now we need to find the hydrogen peroxide concentration here. So what this is asking is, okay, the natural log of H2O2 is negative 3.2. That means that e to what power is equal to negative 3.2. That's what it's saying. So when you need to solve for the variable, you're taking the natural log of an unknown and you need to find that unknown, raise both sides to the power on e. So e to this side means that the natural log is going to go away. We're just going to have the H2O2. It's called taking the inverse log. And then on the right side, it's e to that power. So on your calculator, find the ln button. Go ahead and take your calculator out if you don't have it out already. And not your phone calculator. That Apple calculator is not great. Yeah, you can turn it sideways. Find the ln button. And then on the body of the calculator, right above the ln, not the button above it, but right above it, where you have to hit second function ln, should be e to the x power. So what we do is we just enter second ln gives me, your calculator says e to the power, and then you just enter negative 3.2. And the answer is hydrogen peroxide concentration is equal to 0.041 molarity. Yes?
You have to, wait, how did you get the 0.0008?
The Excel graph gave that to us.
Oh, that was fun.
Right there. This is our integrated rate law. Y is the concentration, the natural log of the concentration. And then K is 0.0008. X is the time. Remember, it's negative KT plus natural log of the initial. So, yeah, this is the K value, that's the time. Does this answer make sense? Is it a reasonable answer? Ask yourself that when you have to determine these things. So at 4,000 seconds, I want you to notice what we have over here. The time is going up, the concentration of the reactant is going down. Over time, the reactant's getting used up. So at 3,600 seconds, the concentration was 0.05, and it was going down. So if I go even longer in time, would we expect the concentration to continue going down? Yes. And sure enough, it does. From 0.05 to 0.04 something. So we see that the concentration continues to go down. This answer is reasonable. Yes?
So since the integrated rate law is in the first order, for the differential rate law, would it be K times the concentration of hydrogen peroxide
To the first power, yeah. Yep, exactly. That's the differential rate law. Yep. Very quickly, one other example. I didn't get to this yesterday. I don't remember why, but we wound up taking too long yesterday going over the test or me chasing you down. So here's another example. We have a reaction in which we have C4H6 becoming C8H12. This is pixelated, sorry, that doesn't look good. And there's data for time versus the concentration of the reactant. Concentration of the reactant starts high and goes down. I don't know if you can tell, but the concentration is getting smaller. So we don't see what the question is yet. The question is right there. Determine the form of the rate law. That's the differential rate law. And then it says find the integrated rate law. Okay, we can do that. So what we need to do is we need to take our handy graphing app and graph out the concentration versus time. That's one graph. Then the natural log of the concentration versus time. Then the inverse of the concentration versus time. Do all three graphs, determine the one that's linear. So I've done that too. And that is on this tab. Oops, get that out of there. Well, What? Oh, okay, didn't need that. So I have two of the graphs. Take a look at what I have here. My zero order graph is just straight up concentration versus time. You can tell that's not linear. So I kept that one small. My first order natural log graph is here. Look at those points in that line. Oh man, that looks very linear. That's nice. Yeah?
That's the wrong graph. That's H2.
It's the wrong graph. Thank you. Sorry guys. And what did I do?
I think you deleted it by accident. Command Z.
Control Z.
Command Z.
Let's see. This is auto saving, so give me a second here. I'm gonna go back to before just now. Okay, there it is. All right, so maybe I'm going to make this graph, this zero order graph, just a little bit bigger. Oh, I'm read only, aren't I? Okay. Okay, there we go. Okay. Hurry up. Come on. Ah!
You have to save.
Oh, man. I don't want to. Okay, well, we're just going to have to move on because I'm going to run out of time. I want you to look at that and tell that that is not linear. Are we all in agreement that that small graph is not linear? Okay, and then when we look at this graph, those points line up in a pretty straight line. And then these points line up in a pretty straight line. So we have first order and second order graph looking like, well, they both look pretty linear. That's where the regression is very helpful. So when we look at the regression on these, this one is 0.9852. 0.98 is pretty linear. But then we look over here, 0.9995. That one wins. Even though this one was pretty good, this one is very good. Yeah.
How do you figure out the regression or will it tell you? Like when you,
On the test,
but like in general, like.
you have the computer tell you.
Oh.
Yeah, yeah. So with the Mac, I double click on one of the points and you'll get this little menu here and you go to trend line and then you'll have a menu over there for the trend line. And one of the choices you have, it'll be at the bottom, display the R squared value, and that's what it does.
Wait,
So yeah, I've done that.
On a test, then what would you do?
So on the test, Are we going to have time to create 3 graphs and analyze them? No. Yeah, I mean, you guys, it's been a long time since you had a hard test, so maybe I will have you do that. I mean, you can handle it. We want to just keep elevating our game, so yeah, do it yourself. Bring an iPad, remember that's in the test. Oh no, I'll have you graph by hand, that'll be even better.
No way this made sense.
No, no.
I can't see that well because the square value is so tiny. But as the graph on the left, the second order, and the graph on the right, the first order.
This is first order. This is ln, so that's first order graph. This is the inverse, so that's the second order graph. And the r squared is 0.999 for this one.
Got it, thank you.
Yep. Okay, so yeah, we have determined this one is a second order rate law. So the rate law equation would be, and that's what it's asking for. The question is, what is the integrated rate law? So it would be 1 over concentration of C4H6 equals positive KT, remember it's positive because the slope is going up, plus 1 over the initial concentration of C4H6. It also asks us in this problem, give the rate laws and the value of the rate constant for this reaction. So we just have our wonderful Excel program. Wrong one. Still wrong one. Yes, this was it. I have the equation for the line, and that K value is given to us. So nice. Back when this book was written was like 2013, people were able to graph on calculators, but the use of the iPads and laptops was not even close to what it is now. I mean, COVID really propelled our use of the electronics in class. And so the expectation back then was you were probably graphing by hand. In the short time, like 15 years I've been teaching this class, we started graphing by hand. We would have to literally calculate each of these values by hand and graph them. It was good, fun. So we went through a lot of graph paper. But what's that? Yeah. So there's a lot more work involved. Be very thankful that you're doing this when you're doing it. Yeah.
So for this homework problem, do you have to graph it? Like, can we do it without graphing? Like, have 3 equations, use this table to find K value, and then plug in.
I think it would be faster just to do the graphing.
Okay.
I guess it can be done if you try to fit the data to each of the graphs. I would just make the graphs. Okay, now we have like 6 minutes left in class. I would like to. I'd forgotten. I just walk right up to the screen. Okay, there you get to look right at my nose. Sorry, Thanos and Kareem. We were missing Kareem and Ali. A bunch of you are going to be watching this.
How are
And
you feeling, guys? How are you guys?
yeah, get better. Anyway, one other thing that will be on the experiment for Monday is I'm going to ask you to monitor a reaction. You're going to make a data table, much like what we had here. So we'll have concentration and time data, and then you'll be asked, what is the order, and write the integrated rate law, so you have to make the 3 graphs. But I'm also going to ask you, I'll ask you to find the K value, which Excel will do for you, or whatever app you use. Another thing is going to ask you, what is the half-life of the reaction? The half-life of the reaction is going to tell us how long it takes to use up half of the original amount of reactant. So if you started with 1 molarity for your beginning concentration, how long does it take for it to go down to 0.5? That's the half-life. And then the second half-life would be how long does it take to get from 0.5 down to 0.25 for that to get cut in half. So we can do sequential half-lives too. We need to know what half-life is. So that's my last thing for today. Oops. Half-life is defined as how much time, remember half-life is an amount of time. How much time does it take to cut our original concentration in half? So the half-life gives us an indication of how fast the reaction is too. But I want you to keep in mind, half-life and rate are not the same thing. They're inverses of each other. The faster the rate, the shorter the half-life. Right? Think about it. Make sure you can process that in your brain. The faster the reaction is going, the less time it takes. So if rate is high, half-life is small. They're inversely related to each other. I'm going to come back to that point at the end of this because you're going to see mathematically we're going to work that out, and then you'll be able to see, yep, I see what you mean mathematically. Okay, so taking a look at this scenario here, it says we have a definition of half-life. It's how much time it takes to cut the original amount in half. So at the half-life, the concentration of the reactant is 1/2 of what it was at the beginning. That's what half-life means. So if I have a first order reaction, let's say that this reaction is first order for A. That means that the natural log of A equals negative KT plus natural log of the initial concentration. That's the first order rate law. I'm going to derive the half-life of this one. It only takes a couple of steps. I'm not going to derive the others. It's real simple, though, to derive them. The first order one, though, is kind of special because most reactions are first order. The majority of them are. If you have to guess, guess first order. If you have nothing else, if time is running out on this test, guess first order. So that means I'm just rewriting the rate law. ln of A equals negative KT plus ln of A0. Now, at the half-life, that means that A, concentration of A, is 1/2 of what it was originally. So, if I'm looking for what the half-life is, I'm going to try to use the equation to solve for the time. And the time, the half-life time would be when this number is half of what that was. So putting numbers into this thing, I'm going to say ln of A's, make this look right, ln of A0 over 2. Right, I said that the A is 1/2 of A0. This is the same thing. 1/2 times A0 is the same thing as A0 divided by 2. Yes? Yes. And that's equal to negative KT. I'm going to give a special notation to that T as well. I'm going to call it T1/2, as in, okay, this is the half-life, how much time it takes. So yeah, the initial concentration just got cut in half. And then we have the plus initial concentration, ln of the initial concentration there. So I'm trying to solve for this thing. How long does that take? Even if I don't have numbers, we can still do it based on the symbols. So now, my students passed Algebra 2. What do I do with this? Natural log of that divided by that is the same thing as A0 minus ln of 2, yes? Okay, so that's why I'm going to expand this. Ln of A0 minus ln of 2 equals negative K times T1/2 plus ln of A0. Do you see anything that can be cleaned up very quickly and easily on this? Both sides have something in common, ln of A0. So subtract ln of A0 from both sides, it's gone. So now I have negative ln of 2 equals negative K times T1/2. I'm again trying to solve for this T1/2. Divide out the K, and divide out the negative sign. We've got negative on the left and negative on the right. So, no, I'm sorry, you guys. Okay, so this is how we find, this is very simple. The half-life is the log of 2 over K. ln of 2 is a constant value, so it's real simple to calculate. Now, all right, it turns out that the different orders have a different calculation of half-life. This is just for first order. I'll give you the other ones on Monday before we do the lab.
Like you would start from that equation.
Yes, yeah, just make A equal to 1/2 A0. I wind up having to drive it every time because I can't memorize it. All right, you guys online, thanks for doing this.
I'll send it to you guys. Hold up.